Right. Let's just define a few terms that we'll use. For mirrors and lenses, the object distance is the distance from the lens or mirror, or the mirror or lens to the object. And the image distance is the distance from the mirror or lens to the image. All right, we're going to call the object distance P and the image distance Q. That's pretty standard, P or Q. You might also sometimes see it referred to as DO for object distance or DI for image distance, but we'll use the P and the Q. All right. And then we're going to have some notations for each of these depending on the signs. And this is really where students sort of flub up a little bit, is they get the signs wrong. And we'll go over the signs and sort of what they all mean, and then I'll provide you some tables along the way that sort of summarize what the signs mean. So if Q is positive, the image is what we call a real image. It's real. Yeah, so if Q is positive, it's a real image. And real images can be projected onto a screen. So for example, this is a real image. The other type of image is called a virtual image, which we'll see in just a second. And a virtual image, on the other hand, cannot be projected onto a screen. Where's an example where you see a virtual image? Right, that's an image that cannot be projected onto a screen. In mirrors, in flat mirrors in particular. We'll see some mirrors that actually do produce real images, but those are curved. So like you can look in the window and see there are images there, not through the window, but the reflection in the window is a virtual image that can't be projected onto a screen. But this, on the screen here, is a real image because you are projecting it onto a screen. Y'all did this in lab when you did, what did you do, like the little screw on the light bulb? Right, that's a real image. If Q is negative, the image is a virtual image. And while you can see the image, like in a bathroom mirror, you cannot project it onto a screen. Right. The virtual image, that's like in that movie Poltergeist. You ever see that movie? How would you say, what? The light, go to the light. That lady. Y'all seen the movie? It's from the 80s, I think. The people in the mirror. Yeah, it's still kind of scary. My wife doesn't watch scary movies. I haven't watched a scary movie in like 12 years. Huh? Okay. All right, so if Q is greater than 0, that's a real image. If Q is less than 0, it's a virtual image. You'll need to keep that in mind. We'll also see different types of mirrors produce these different kind of images, and you'll need to know the scenarios in which they create those images. So we'll go over that quite a bit. Flat mirrors are probably the easiest. I go down from here. For flat mirrors, your rule is that Q is equal to negative P. So if you imagine that you have this flat mirror, like in Harry Potter, right, when he stands in front of the mirror and he sees his parents in the mirror, yeah, okay. So he stands a certain distance in front of the mirror. This is our object distance. And then behind the mirror, this is his image. Right, and this is the distance Q. And so for flat mirrors, we would say that Q is the negative of P. That means that the same distance is between the object and the mirror as is between the image and the mirror. Right? The image is an equidistant from the mirror as the object is from the mirror, except that it's negative. And so the negative comes into play because this is what type of image? This is a virtual image. So we just have that negative there to remind us that this is a virtual image. So this is a virtual image. Give me just a second. I'll come back and we'll play this little clip by Richard Feynman just about mirrors. It's kind of cool. All right, so we're going to do it now.
Another British man?
No, he's American. He's dead. we have if this is our object, right, and this is our image height here is less than 0, it's negative, and our magnification is also less than 0, it's negative. Yeah?
How about the magnification of -1? Did it include what equals -1?
If the magnification is -1, it means that the image is the same size as the object, right? Because the magnitude of the magnification is 1. All right, but it means that the image is inverted. All right. So as I've drawn this one, if hi is equal to ho, which it looks like it is, this would actually be a magnification equal to -1, because the image is the same size as the object, but it's upside down. We don't usually see that in mirrors, or we never see that in mirrors. And no, we can. Yeah, we can see it with. Pretty sure you can. I'll have to think about it. I forget. Anyway, we'll see it more with lenses. Yeah.
If the magnification is higher, does that mean Q's or P is bigger?
Right. Yeah. So magnification is also related to Q and P, which we'll see. But for a flat mirror, because Q is equal to -P, it's always going to have a magnification of 1, of +1, because Q is always equal to -P. So no matter how far you move from a flat mirror, your image is always going to be the same size as the object.
Can it ever be Q equal to +P?
For a flat mirror?
Just for case.
Yeah, I mean, you can have yes, you can have the image and the object at the same place. Oh, no, I'm sorry. Yes, you can have that. We'll see it when we get it. You have to have a curved mirror in order to have that. All right, yeah, so we'll see that. Here's just a little summary of all that. So this is the magnification. This is actually the absolute value of the magnification. Or actually, let me rephrase that. If the absolute value of the magnification is greater than 1, it's a bigger image. If the absolute value of the magnification is less than 1, it's a smaller image. That means that it's between 1 and -1, right? It's 0.5, it's -0.5, whatever. If the magnification is equal to 1, it's going to be the same size image. If the magnification is positive, it's upright. If it's negative, it's inverted. All right. We've also seen some other things that, and you might want to just rewrite them here. If Q is less than 0, that is, it's negative, it's a virtual image. If Q is greater than 0, it's a real image. So all these sign notations become very important when you're working through these optics problems, as we'll see. We'll do some later. All right. Now, there is a relationship also between M, Q, and P. What do you think that is, just based on what we know about a flat mirror? And remember, what we know about a flat mirror is that M is equal to +1, and we also know that Q is equal to -P. So what do you think is the relationship between Q and P for the magnification? For M, Q, and P. Well, you've seen it in lab, right? Right, so the magnification is not just Q over P, but what? Because if it was just Q over P, that would say that the magnification of a flat mirror is -1. -Q over P. Yeah, so our magnification is -Q over P. And this is going to be for flat mirrors, but it will also be, hey Jose, it'll also be for all mirrors, for curved mirrors, spherical mirrors, and also lenses when we get into lenses. All right, so the magnification is equal to -Q over P. So this is for mirrors and lenses. And then for images and flat mirrors, just to sort of summarize what we've had, these things are true, that Q is equal to -P, and then also the magnification is equal to 1. All right, that means that your image is always the same size as the object. Image is always the same size as the object. We'll see that a little bit later in the concept test and some of the implications of that. That the image is always the same size as the object. All right, we're going to do some ray tracing in this class. Y'all have already done this in lab, and this first part is just like what y'all did in lab if you're in the lab. When we're doing that, we're going to first just need to remember the law of reflection, and this will hold true for a flat mirror. It holds true for spherical mirrors as well, but particularly for flat mirrors, and that's just that the incident angle is equal to the reflected angle. And we just had this, so if I have a certain angle that a light ray is coming in, I'll call this theta I, and this angle, theta R, is going to equal that. So theta I will equal theta R. So when we're drawing rays, like this for example, I have a star right here. I want to know where the image of that star is. Now I know for the flat mirror that if this is my object distance. What do I call it? This distance, what do we call it? The object distance that the variable is. The object distance is P, right? So this is P. And then I know that my image is going to be over here, equidistant from the mirror, and that's going to be Q. But I just want to verify that by drawing rays. And so this is called ray tracing. It's not terribly difficult with flat mirrors. It's pretty simple. But we'll do a similar thing with curved mirrors and with spherical lenses and mirrors. So you draw one ray that originates from the object. Doesn't really matter where you draw it, but when you draw it such that it follows the law of reflection. Oh, that's not very good. It's better if you have a ruler when you do these. So there's my first ray, and if I want to know where the image is, I trace this ray back. And the image will lie somewhere along this ray that I trace back. We call this ray, by the way, a virtual ray, because it's in that sort of world where the poltergeist people live, right? That there's people that roam around in the black suits. That's called a virtual ray. That was a joke, right? There's really not a virtual world where that was just a movie. All right. Right. Okay, and then we don't really know where it is because this star could lie anywhere along that virtual ray. So in order to actually locate the position of the object, or the image, we have to draw a second ray. So I'm going to draw another ray right here. And notice this has a much smaller incident angle, so it'll have a much smaller reflected angle. And then I can trace it back. And wherever those two rays cross is where my image is, which is where we said it was going to be anyway. All right, y'all did this in lab with protractors and rulers and all, so you were able to show then that Q is equal to negative P. But just sketching it out, you can see that as well. Likely on the next test, you'll have to draw some ray tracing diagrams, probably not for flat mirrors, probably for curved mirrors, spherical mirrors. But the idea is very similar, that you draw two or more rays, and where the rays cross is where the image is. What type of image is this? This is a virtual image. And virtual images are formed by virtual rays. All right, so we call these dashed rays virtual rays because they don't really exist in real space. They're sort of behind the mirror, if you want to think about it in that way. But they're formed by these virtual rays, these virtual images. And remember, you can't project these onto a screen. By the way, we'd call these over here real rays. And they would, if the rays crossed on that side of the mirror, then they would produce a real image, which you could project onto a screen. Okay, so Okay, I'm sorry, this is where it's going to do that. All right, so you just draw two rays. All right, so let's try this quick test. I have two people that are observing a rock in a flat mirror, and it says that person number 2, this is my object, person number 2 sees the rock at position C. Where does person 1 see the image of the rock? If you're uncertain, you can try tracing out the rays that person 1 will see. Where does person 1 see the image of the rock? And remember, for flat mirrors, that Q is equal to negative P, and that's always true. Q is equal to negative P for flat mirrors.
Oh, where's the person from?
Huh? Yep. All right, just a few more seconds. I'll stop at 122. All right, C is correct. A few of you are missing this. If it helps you to remember this law for flat mirrors, notice that for Q to be equal to P, for the magnitudes of those distances to be the same, they have to be directly across from one another. Because notice, if we had the image distance here, which is the distance from the object, or from the object distance here, that would not be the same as that distance. So the point here being that we always measure the distances actually in a line that's perpendicular from the object. All right. So Q is always equal to negative P, and so no matter where you are with relation to a mirror, the image is always going to be in the same position. It doesn't matter where you're observing it from. That is always, the image will always be where it will be. And what is the magnification of a flat mirror? Where magnification is negative Q over P. Right? And for a flat mirror, P is equal to negative Q, or Q is equal to negative P, however you want to say it. All right, there's a few more seconds. I'll stop at 40. I think it's right. Magnification is equal to positive 1 for a flat mirror. In a flat mirror, you're always the same size as the object, and you're always upright. Right. Flat mirrors are pretty simple, right? They're just some basic ideas, but we'll use some of those ideas for spherical mirrors. Spherical mirrors are a little more complicated. When you think of spherical mirrors, you think of them being cut out of like a big ball. So let's say you have like a big spherical piece of glass that's hollow on the inside, and you just take it and you slice off the end of it. So if you were to slice off part of this, then you would take that piece and then you would have a spherical mirror. That's why we call it spherical. There are other mirrors that are parabolic in shape. So instead of being sliced off of a sphere, they're made into the shape of a parabola. And then there are some other types of mirrors as well, which we'll talk about later. Now, if the inner surface of the sphere is reflecting,
Yeah, I know.
it's a concave mirror. What's up, Scott?
I know they Mythbusters did a sense of they wanted to have creations of different mirrors to burn a smaller boat, and they had someone who made a parabolic mirror by taking a reflective material, kind of like aluminum foil, really shined up, and they put it over a 5-gallon bucket and sucked in a vacuum, and it made a parabolic mirror.
Okay.
Sounds stupid, but it works.
We'll talk about parabolic mirrors later. They're kind of cool. All right, so if the inner surface of the sphere is reflecting the mirror, we call it a concave mirror. I always remember this if you ever forget, because concave, I always think that it caves in. It caves in. You'll see what I mean in a second when we show you a concave mirror. And next time I'll bring a concave mirror. We're going to wrap up pretty soon, but next time I'll bring a concave mirror and we can take a look at it. A concave mirror, by the way, is where do we experience that? This is where the reflecting surface is back here, so this would be like the back of the mirror. Whatever you put on it, silver paint, some sort of reflective surface. Aluminum, yeah. So this is the reflective surface. And so if your object would stand over here, so you stand on this side of the mirror, this is a concave mirror. And where do we see concave mirrors? You don't see them very often, but there are a few cases where you see them sort of in your life.
I feel like your car mirrors.
One of those fun houses in the.
We have a fun house, but who goes to a fun house that often?
Well, those are the school and they oversee it.
Okay, those are convex mirrors, right? So they're the opposite side is reflective. Like you would stand on the bulbous side, right, of that mirror.
Like, ladies use those makeup mirrors to make them see closer.
Right, yeah. Ladies use those makeup mirrors so you can see your face all blown up with all the pores and the dirt and the grease and stuff. So I don't know why people do that. I'm sure y'all don't do that, but yeah. So those are concave mirrors, and in fact, yeah, and your dimples. I can see your dimples too. If you get far back from a concave mirror, you'll actually find that you're inverted. So that if you have one of those mirrors, they're kind of fun because you can back up far away from them, and then you'll be upside down.
I have one in my Firefly one.
So what is like?
No, those are convex mirrors. So we'll see that in just a second. I have a big concave mirror I'll bring next time. We'll take a look at.
I have one in my firefighting light. They use the reflective surface, the LED, and it's a concave mirror. If you look into it, it's not with the light on.
Right, because it brings light together. All right, so at the outer surface of the sphere, what? That doesn't make, if the outer, this part is a reflecting surface, it is a convex mirror. I'm sorry, that doesn't make any sense. So basically, if this now is the reflecting surface, like this is the back part of the mirror that is painted with aluminum or whatever, and you're standing on this side, right? So this would be your object distance P. This is called a convex mirror. And this type of mirror, several of you have said, this is like a security mirror.
Yeah, the ones that in the corner of the stores.
Right, the kind they have in the corner of the stores. It's also like on your, where? On your car? Yeah, on the right-hand side of your car mirror. So it's also a car mirror. They're usually just on the right-hand side. That just allows you a greater field of view so that you can see cars coming up beside you. You can also take a little mirror and attach it to your left-hand side, which is just a type of convex mirror. All right, so convex mirrors are a little more common. I'll just show you this one more thing, and we'll stop at the mirror equation, which we'll pick up next time. So for both types of mirrors, whether they're concave or convex, we're going to describe a couple of things. Remember, we're taking these out of a sphere, right? So it's like I've cut these things out of a sphere, or a slightly lopsided sphere, as you will. But a sphere is defined by a radius. And we're going to call the point, the distance from here to here, we'll call it C. And C is called the center of curvature. That's just the radius of the sphere from which you've cut the mirror. So it's not some small radius, it's the radius of the big sphere that you've cut the mirror out of. And then we'll also define the focal point, which is half of the radius of curvature. So that's the C. We'll also define the focal point. So F is called the focal point. It's also called the focal length. Those are basically the same thing. though technically the focal point is the point of F, and the focal length is the distance from the reflective surface to that point. Right, so we can define them geometrically in that way. That the center of curvature is the radius of the sphere, and the focal point is 1/2 of that center of curvature. So F is equal to C over 2, half the radius. We can also define the focal point as where the parallel rays converge, where they focus, which is why it's called the focal point. When you get parallel rays, they'll come in like this, and then they will focus at the focal point. No matter where they come from, or where they strike on the mirror, they will always focus at the focal point. Parallel rays will always focus at the focal point. So this is a different way of defining what the focal point is, not geometrically, but how light behaves when it strikes a reflective surface. And then finally, rays are parallel when they originate from some source very far away. You can imagine this, like say you have a light bulb. Right, it's putting out light rays in all directions. And if you're standing up close to the light bulb, you'll see light rays that are going in this direction and that direction, right? But they're not parallel. But if you stand really far away from a light bulb, or like if you stand really far away from, I don't know, the sun or whatever, by the time the light rays get to you, they will be parallel. Because you're seeing two light rays that originated at basically the same point on that source of light. All right, we're going to pick up next time with the mirror equation. Yeah, Jose? Sure. You have a question or?
No. Okay.
Okay. We're going to do evals. We haven't done them yet, right? No. No evals? So we have about 15 minutes left. Let me just sort of give you a quick primer. I know y'all done evals. Let me talk for just a second about them and the purpose.